Hello and welcome to Blue Marble Science. In 1798, Henry Cavendish accurately measured the density of the Earth for the first time. His effort remains an iconic example of the scientific method and a pattern for the experimental process we use to this day. In this video, we're going to examine the methodology of Cavendish and explain his approach to the determination of Earth's density. In the late 1700s, Reverend John Michell of the Royal Society had contrived a torsion balance for the specific purpose of measuring the density of the Earth, but had been unable to conduct the experiment before his death. Cavendish acquired the device by way of Reverend Francis Wollaston, Jacksonian professor at Cambridge, and decided to rebuild the apparatus and conduct the experiment himself. The torsion balance is a horizontal pendulum, and it's very similar in operation to the simple pendulum you might find in a clock. The major difference is in the source of the restoring force that returns the pendulum to its starting position. With a simple pendulum, that force comes from gravity. When the pendulum is forced out of its resting position through an angle we'll call theta, gravity returns it to its resting position. But with a torsion balance, which is a horizontal beam with masses attached at each end and suspended in the center, that force comes from the torque induced in the torsion element, which is usually a fine wire or a ribbon. When the balance is forced out of its resting position and rotated through angle theta, the torque that rotation produces in the wire returns it to its initial position. But a pendulum of either type is a simple harmonic oscillator. Now, we've all experienced the way these things work. Take any weight hanging from a string and pull it off center, and when you let go, gravity pulls it back towards its resting point. But you'll see that the inertia of the weight causes it to overshoot. Once it swings beyond its resting point, gravity now slows it down until it reaches a point on the opposite side that's just a little less displaced than the amount you moved it to begin with, and it reverses direction and repeats the process with each displacement becoming just a little less. This is what we call a damped oscillation, and you'll note that the period of the oscillation doesn't change, even though the magnitude of the swing is decreasing. This holds true as long as the initial angle of displacement is relatively small. And it's this property of pendulums that make them so useful for timing. The pendulum formula is very simple, and we can determine the period of oscillation just by knowing the length of the pendulum and the local value for little g. We define a thing we call a seconds pendulum that has a period of 1 second from one extreme point of the swing to the next extreme point of the swing. In other words, an overall period of 2 seconds. That period is 2 pi times the square root of the length of the pendulum divided by the acceleration of gravity, and it's slightly less than 1 meter or just a little over 39 inches, depending on the actual value of little g where the pendulum is located. Cavendish relates the period of a seconds pendulum to a torsion balance of length L so that he can find the restoring force, F sub theta, required to pull the arm through angle theta. At his location, the length of a seconds pendulum was 39.14 inches, and his balance had a length of 36.65 inches. He reasoned that if the stiffness of the torsion wire was such that the ratio of the force required to pull each ball a distance A to the weight of the ball, and that would be F sub theta divided by mg in our diagram, is equal to the ratio of distance A to the radius of the balance, which is 36.65 inches, the balance will vibrate in the same time as a pendulum whose length is 36.65 inches, or the square root of 36.65 divided by 39.14 seconds. He's simply saying that if the force required to rotate the torsion balance through angle theta is the same as the small lateral force required to pull a seconds pendulum through angle theta against a force component resulting from the downward force of gravity on the ball, the torsion balance has to vibrate in the same time as a simple pendulum with a length of 36.65 inches. Cavendish then reasoned that if the torsion balance wire stiffness is such that the torsion beam oscillates in a period of n seconds, the ratio of the force that must be applied to each ball in order to draw it aside by a distance a to the weight of that ball, and again that's F sub theta divided by mg, must be equal to the ratio of distance a divided by the square of period n times the ratio of 36.65 divided by 39.14, and all of that divided by the distance from the center of the arm to the scale at the end of the arm, and we'll call that distance r. Now recall previously that n is equal to the square root of 36.65 divided by 39.14, and a divided by r is simply angle theta. So what Cavendish has done is normalize an expression that you see at the bottom of the slide, and that's 1 equals 1 divided by n squared times the length correction of 36.65 divided by 39.14 for his pendulum length. We're going to use this expression in a minute. We need angle theta not stated as an angle, but stated as a deflection of B divisions of the torsion balance. For making the measurements, Cavendish attached ivory strips to the balance arm a short distance beyond the point where the small balls were attached, resulting in them being 38.3 inches from the center of the beam. Now that's the distance R we've been talking about. The scale he used had divisions of 1/20th of an inch. So for a 1 division deflection of the beam, angle theta can be closely approximated by simply A divided by R, or 1 divided by 20 divided by 38.3, which is 1 divided by 766, or B divided by 766, where B equals the number of divisions the beam moves. Now, all we need to do to find the force that is required to pull the balance from its resting position is to multiply that expression, B divided by 766, times the normalized expression we developed a minute ago, and we find that force is equal to B divided by 818 n squared. Looking at this in a more conventional sense, what Cavendish did was equate the formulas describing a simple pendulum and a torsion pendulum, and when you do that, you come up with the expression L over G equals I over K, where L is the length of the pendulum, G is the acceleration of gravity, I is the moment of inertia of the beam, and K is the spring constant. But I is the moment of inertia of the balance, which, in simplified form, is the mass of the small balls multiplied by their distance from the axis of rotation squared. Now plugging that in gives us L over G equals mL squared over K, and we can simplify and rearrange those terms to give us 1 over mg equals L over K. But the force required to move the arm 1 division, F sub theta, is equal to K, the spring constant, times theta. So solving for K and substituting that in the previous expression gives us F sub theta divided by mg equals theta L. Then we have the same normalized expression we derived earlier. If we multiply the right side of the force expression by the normalized expression, we end up with F sub theta divided by the weight of the ball equal to theta L times the unity expression of 36.65 divided by 39.14, all over the period of vibration squared. Theta L is simply the displacement of the arm, and as before, this ends up being equal to B divided by 766, where B is the number of divisions. We only need to substitute that for theta L, and we get the same answer Cavendish came up with, or the force required to move the arm through one division divided by the weight of the ball, mg, equals b, the number of divisions, divided by 818 n squared. If your head hurts at this point, think how mine feels. Next, Cavendish corrects for an oversight made in the construction of the apparatus. Cavendish had made the distance between the centers of the large masses exactly the same as the distance between the centers of the small masses, and this resulted in the large balls not being in line with the small balls when they're in their resting position. Now, I won't go through the details of how the correction is derived, other than to say that this misalignment effectively reduced the apparent mass of the large ball by a factor of 0.9779, and that's significant enough to require inclusion in the calculation. Now, the final step is to find the density of Earth in units of water density, in other words, the specific gravity of the Earth. Cavendish knew the mean diameter of the Earth to be 41,800,000 feet. The weight of the large masses had been measured to be the equivalent of 10.64 spherical feet of water. The actual distance between the centers of the balls was 8.85 inches, but Cavendish wants the equivalent force at the surface of a 12-inch sphere. So Cavendish corrects the effective mass of water for this distance, as well as the misalignment between the balls, and finds the attraction of a particle placed at the center of the small ball to an equal particle placed at the surface of the large ball to be in the following ratio: 10.64 spherical feet times the 0.9779 correction for misalignment times the ratio of 6 inches divided by 8.85 inches squared. And that ends up being 4.782 to 1. Therefore, if the ratio of the mean density of Earth to water is equal to D, the ratio of the attraction of the large mass to the small mass to the mass of the Earth will be 4.782 divided by 41,800,000. And that's equal to 1 divided by 8,739,000 D. This is the number Cavendish got. You'll actually get a slightly different number if you use a calculator, but we'll just go with what he had. So finally, if the force that must be applied to the balls to move the arm one division is B divided by 818 n squared of the weight of the ball, and that's what we found earlier, and the attraction between the balls is 1 divided by 8,739,000 D of the weight of the ball, the attraction that will move the balance one division is F sub theta equals B divided by 818 n squared, which is equal to 1 divided by 8,739,000 D. And if we simply cross multiply, you end up with 818 n squared divided by 8,739,000 D times B. And solving that for D and reducing the fraction, we get n squared divided by 10,683 B. Wow. At this point, Cavendish lists 6 potential systematic errors that he wanted to account for. Now, most of these have very little effect on the final value of density, but we'll run through them quickly. First is the inertia of the wooden beam. When we calculated the moment of inertia of the beam, we considered that the beam had no mass whatsoever, but the beam does have mass, and that affects the oscillation period, and that needs to be corrected for. Secondly, Cavendish accounted for the attraction of the wooden beam itself to the large balls, and it turns out that that attraction is negligible. Third, he accounted for the attraction of the far ball. In other words, the large ball attracts not only the small ball that it is closest to, but it also has a slight attraction on the far ball away from it, and that attraction is in the opposite direction. So that has to be accounted for. Fourth, the attraction of the brass hanger rods, and that was found to be negligible. Fifth, the attraction of the case itself, and again, that has essentially no effect. And finally, sixth, the position effect on the period of oscillation. Now, this does have an effect. If the large balls begin in the neutral position and are then moved to a resting position, it will affect the period of oscillation. On the other hand, if the large masses are moved from one resting position to the other, and the period of oscillation is measured while the masses are in those positions, there is no need to make any correction. When we take all of that together, Cavendish combines these corrections and arrives at this final expression of D equals n squared divided by 10,844b, where n is the period of oscillation, b is the number of divisions of movement of the balance, and d is the specific gravity of the Earth. This is a summary table of the experiments Cavendish performed. He has a total of 17 experiments and a total of 29 different tests. Let's take one experiment as an example. Experiment number 12. Cavendish lists the time of vibration being 7 minutes and 3 seconds. Don't be fooled by the comma. He uses that as a separator, but he is giving it to you in minutes and seconds. He also lists the motion of the arm as 6.09 divisions. Now, because of the way Cavendish set up his math, when the masses are moved from one extreme point to the other extreme point, you actually have to divide that motion by 2. So instead of 6.09, we need 3.045 for the value of B. Now, when we plug those numbers into the expression Cavendish derived, you end up with a density of 5.42, which is exactly what he says in his table. The average of the density values for a series of 29 tests performed by Cavendish is 5.48. Today's standard value is 5.513, or about 0.6% higher than the density measured by Cavendish. And I think most would agree that this is a truly remarkable accomplishment for a gentleman operating under what we would consider relatively primitive conditions in the late 18th century. But wait, there's more. A little less than 100 years later, Charles Vernon Boys came along and is generally the guy that's given credit for establishing what we know today as the universal gravitational constant, or Big G. And while this is quite true, I can also argue that Cavendish did everything but write it down. And here's why. Cavendish knew the diameter of the Earth as well as the acceleration of gravity here on the Earth, and now, having measured the density of the Earth, he knew the total mass of the Earth. From Newton's equations, if we insert Big G as Boys did, we can derive the following expression. Big G is equal to little g times r squared, that would be the radius of the Earth, divided by m. The mass of the Earth is 4/3 pi r cubed times the density of water, and in this case it is 5,480 kilograms per cubic meter. The radius is 6,370,000 meters, and little g is 9.81 meters per second squared. Plugging those numbers into that equation gives you a value of g of 6.709 times 10 to the minus 11th, or within 1% of the accepted value we use today. So that's it, folks. Thanks for watching. I hope you enjoyed it. Thanks for your support. And as always, don't forget to hit those little buttons down there. Special shout out to the patrons and PayPals that have been so helpful to me on this project. And I guess we'll see you guys on the next one.